Hello, and welcome to another episode of the BioHacker podcast. I'm your co-host, David James Clark IV, here with the esteemed Alex Feltus, PhD. How you doing today, Alex?
Excellent. How you doing, David?
Doing awesome. Thank you. I'm really excited about today's triple play topics. And before we get to that, why don't we cue the opening? All right, that's fun. Okay, so today's topic with Ben Sherman is biodata, AI, and workflows. And I called it the triple play because it seems like those are three kind of separate, unrelated topics, but I know in some way you and Ben are going to share with us how they're related. Of course, if you think about those three, the one that jumps into my mind, and I think most people are engaged in on a daily basis, is AI. AI is everywhere. I just went to the city last weekend and got a hamburger made by a robot. So no human hands touched this hamburger, and it was actually very good. I think one of the most common uses of AI is Siri or Alexa. That's becoming more and more prevalent. One of the applications of AI that's near and dear to my heart is learning. As you know, I'm a big digital learning guy, and AI has impacted learning in a variety of different ways. Somewhat, some around conversational chatbots, doing coaching during the learning experience, assessment. You can have AI facial recognition or AI transcribe some video feedback and score it, believe it or not. Of course, AI curation, something you've used in your classes, the idea that AI goes out using machine learning, crowdsourcing big data, finds the best content, delivers it to the learners in real time. So let's start with learning, and then we'll move on to science. What are some of your favorite applications of AI in learning?
Definitely, this content curation is a really cool thing, and it seems very early to me, even though it's very effective. Like, you get really neat content, but if we can get AI to the point where it starts to generate the quizzes and generate labs and things like that, I think it's going to be even more effective. But one thing I look at AI is like, it's a very small amount of code that you can write, and you can learn how to code it in a very short period of time. And it gives you this like tool, this power, this new set of eyes to look at data and find patterns in data, like visually, but also like statistically. And it's really very much common sense. It works kind of like it's designed for our brain, what little we know about our brain. And it's very functional. It's just anything you can do, from my perspective, learning or science, if you can see a pattern, you can get AI to learn that pattern. I mean, AI is driving cars, right?
It's funny, but funny you should mention that one, because that's exactly what was going through my mind. I took that crazy Andrew Ng AI course and got my AI certification, which means very little. But in that, they talked a lot about how AI drives cars and the pattern recognition. And I'm scared to death, obviously, to drive in a self-driving car, but I imagine that over time it's going to get better and better. And I know AI, one thing I learned from that class is AI relies on big data. There has to be a lot of data. The more data, the better. The more data, the smarter the AI. So I imagine that's where the biodata piece of today's episode comes in, is it's AI working on chewing on large data sets from biosciences. Is that right?
Yeah, or you could say large data sets, which is totally accurate, like large for the computer from their perspective, but also just the complex systems. I mean, you're trying to see the weather and you're trying to measure the weather, and you can't, use a piece of paper and a slide rule anymore. You have to have computers and AI to be able to process it. And it's a real quantum leap, because when I first started using the lab, and I'm not a computer scientist, I wasn't trained and all that kind of stuff. I work with people that do that, but I was able to see patterns in my data just by visualizing it, like trying to separate how different things are from all their differences, and just seeing things like tumors and in normal tissues and different types of tumors and how progressed the tumor is. You can see it in the data. So it helps you like go from like, I have no idea what the data I'm looking at because it's so big, to I can see there's differences. So explaining those differences, it kind of goes back into science and hypothesis testing, and also kind of really one of my favorite tools in science is common sense. And like
Yeah.
these things are different, and what is it? And just trying to figure it out. That's the Alabama in me.
Yeah. It's interesting when you're talking, I'm thinking about the self-driving car, and one of the key things there is being able to, scan the environment and identify patterns, what's a tree and what's a human and what's a road. And I imagine that same concept applies when you're, scanning big data sets, biological systems, and
Yes.
identifying different cell types and looking for patterns, pattern recognition.
Yeah, I mean, actually, our guest, Ben Sherman, he's somebody I met years ago, and he was in a lab where they were doing self-driving cars work.
Oh,
A bunch of computer engineers, and it's a lab that I worked with the person for a long time, the PI, the principal investigator of the lab. And I walked into the lab one day, and they had Grand Theft Auto playing on a screen, which is this video game, right, where you go and do all sorts of stuff. And kids, you have to be 40 plus to be able to play this thing, but
I know.
everybody's going to be playing it. But they had a camera watching the video of a car driving, and they actually were using AI to control like the controller, like the handheld controller you would use in the video game. They bypassed that, and they were controlling the car with the camera. And this is back when I first met Ben and some other people in the lab. If maybe a few months later, one of the students in the lab said, well, there's a way to trick the self-driving car to where it doesn't know that there's empty road in front of it, so it just veers to the right and the left and crashes. And it's something that some people have developed to be able to hack into some of these artificial intelligence models. And he's like, well, could we do that with normal and tumor data? Like where the normal data has been tricked into being tumor, and just do the exact same thing where you treat the data like an image instead of like an image of what's in front of you. And then we did that. We published a paper on it, and we're actually publishing multiple papers on it. It's a very practical, common sense type of science that I could never do without these tools that I guess I understand about halfway.
Yeah, but well, our guest, a great transition, because our guest Ben Sherman understands them a little more than halfway. So
Yes.
let's welcome Ben to the show. Hey, Ben, thank you so much for joining today. We've got Ben Sherman here, who's excited to talk about biohacking and specifically for today's episode, biodata, AI, and workflows. So before we get to those three and what they mean and how they work together, Alex, do you want to do a quick introduction of our friend Ben?
Yeah, Ben is a double Renaissance man. I've known him for several years, going back to when he was an undergrad, and he's an amazing person that's able to do hardcore software engineering and artificial intelligence work, but also is a great people person and can talk complex science with people and translate that patiently, which is sort of the key property. I bet Ben would agree with that. And so just amazing things. And so he really is, I look at Ben as kind of like a third quarter of the 21st century type of scientist.
Oh, wow. Well said. Ben, your rebuttal to that?
Well, that was a wonderful introduction. A lot better than I was expecting. So normally he would just berate me for not being more productive in the lab. So.
I know, yeah, that's right. We love Alex that way. So you've had some pretty exciting activities this year, I think in the last 12 months, if you want to talk about, what you've been up to, because I think you did the trifecta here all in 1 year.
Yeah. So in the last year or so, I got married, my wife graduated, I graduated, defended my PhD. Right as I was doing that, I was also interviewing for jobs, and so I found a job around the same time. And then my wife and I, we'd both grown up in South Carolina, but we decided to move out to Austin, Texas, because my job is remote. So we moved out to Austin, Texas at the beginning of this year, and we've been here for the past 5 or 6 months or so. And that's about all I've been laser focused on is like, man, we did all that. I'm ready to just relax for a bit and just enjoy the ride for a little while before moving on to something else. In previous years, I'm also a a musician. That's probably my main thing, aside from just being a software guy. But PhD and pandemic kind of threw a wrench in that. It's hard.
Yeah.
It was hard to play with people when the pandemic was going on, and that's really the funnest part about it, is when you have other people to play with. A lot like science, it's very collaborative in nature. And also I just had to focus on other things, with the PhD. So that's been on break for a while, but I'm hoping to get back into it once we've maybe settled down a little bit more here, met some people, found some jazz clubs to go to or something. People keep telling me that there's a huge music scene in Austin. I just haven't explored it yet.
I'll tell you what, I've been there plenty of times. I know some musicians who absolutely love the place. They talk about Nashville, being the center point of music. I think Austin's probably the center point of live music. And there are lots of clubs and lots of great opportunities for just about everybody. There's open night mics, all open mic nights all the time. You are going to love Austin. And as you were talking, I pretty much figured that's why you moved to Austin. I'm sure that entered into your thinking.
I'm sure that was a factor.
Yeah. So the question that's burning in my mind, and maybe you can talk a little bit about, your story and how a software engineer gets into AI and then, bioscience, and how you and Alex kind of ended up together. Because it's really a cool story, and I know this paper you're working on. I want to talk a little bit about the cool use of gaming AI in cancer research. But tell us a little bit about your story and how you and Alex hooked up. How you got into biosciences.
Yeah, it's a fun little story. I went to Clemson for my undergrad. Like I said, grew up in South Carolina, so it was an obvious choice. And then I stayed for my master's because I found a lab that I would enjoy working in. And this was Dr. Melissa Smith's lab. And she was doing a lot of work in high performance computing and also starting to get into AI. And around the time I started, Alex came to our lab and basically just presented on what he was doing. He was like, hey, here's all these different projects we're working on. We're always looking for people like y'all to come and help out with the software and the engineering aspects. And I really owe it to my buddy Colin for a lot of things, really. He was the one who got me into the lab. And then he was also the one who was actually like, hey, let's go and talk to Feltus about this. And so I went with him. And that was sort of how we got into the lab, and so we did that for about a year. And then after about a year, I was planning to do a master's. I decided to switch into a PhD. And honestly, the main reason was that I wanted to go get hired by NVIDIA. So we had a lot of guys in our lab who had graduated and moved on to NVIDIA. And they actually gave us a tour one time of one of NVIDIA's fancy new buildings. They built this giant triangular building, and it was just really cool. And they were telling me about all the different work they were doing. And it's like, man, I really want to work for this company. And it seems like they hire a lot of PhDs. So I think I'm going to have to get a PhD, and then maybe they'll hire me. And I knew at the same time that, I'd been working with Feltus. So I knew that there was going to be plenty of stuff to work on, right? There was going to be plenty of interesting projects. I wouldn't have to do like the typical like PhD nightmare where you're sort of meandering for 6 years looking for a dissertation topic. I think that the topic I ended up doing, I think Alex and I first talked about that within the first year or two of my PhD. And then that was sort of remained the dream and the goal from then on. And so, yeah, I stayed for my PhD. I think I ended up finishing it as quickly as I intended, about 4 years, 4.5 years. I think COVID probably delayed me by about a semester. That and getting married, that was also a big thing.
And that's kind of important too.
we finished it, and I did actually get an interview with NVIDIA and got an offer from them. But around the same time, I also got an offer from this other company called Sakara Labs. They're basically a startup around a certain open source project called Nextflow, which we had been using in our lab. And it was not something that I really thought would ever actually happen. But the funny thing is that they the topic that we settled on for my PhD topic was actually something they wanted to implement in their product. And so basically, once I got my first paper out on that topic, I just emailed it to them. It was kind of a long shot, honestly. I was like, hey, I know you guys want to build this out. I'm actually working on this. Why don't you hire me and I'll do it for you.
I'll build it for you.
just kind of out of the blue. I hadn't really spoken to them that much, and they were actually like, yeah, let's do it. And so I end up going to work for them. Basically a dream job. You get to actually apply your PhD work into a business context and, work on Nextflow, which was a very beloved software project that we used in the lab. And so I'm just having a good time, man. Just hanging out in Texas, working on Nextflow.
Playing in the jazz clubs. I love it. Yeah.
Yeah.
Living the life, man. You're the Renaissance man. Okay, so talk about Nextflow. Talk about the role. I mean, for me, we talk about biodata, AI, and workflows. And earlier, Alex and I talked a little bit about AI. Everybody knows about AI, and of course, data is the fuel for AI. But people, I don't think, fully appreciate the value of workflows and the magic that happens. Nextflow being, as you described, the open source application of that. So talk a little bit about workflows and Nextflow and the role they play in bioscience.
Yeah, honestly, it's hard to put into words, like the experience of discovering Nextflow. And it's not just Nextflow, it's workflow managers in general, of which Nextflow is one of the more popular ones. But there's this there's this thing that happens when you're a computational scientist and you start learning about all these different analyses and tools that you want to use. And usually what happens at first is that you just write a script that change all these tools together. And it can be a really big hassle trying to get these giant scripts to run on supercomputers, or especially in the cloud. Like, forget about the cloud. Like, that's just not going to happen in this situation, right? And then you come across a tool like Nextflow, and there's others like SnakeMake and BioMake and WDL and all these other ones, but just Nextflow in particular, we'll focus on that, where it's like, here's a language where you can define, here are all the different steps I want to run in my analysis. Here is how all the steps depend on each other, right? So, you run step A, and then you run step B and C, and they both depend on A, but they're independent, so you can run them in parallel. Try implementing that in a bash script, right?
Yeah,
and then, you got D and C, and so on and so forth. And you just define all that. You just define basically it's like a sewer system, like a pipeline. And then you just say Nextflow run, and you give it your laptop, or you give it a supercomputer or a cloud platform, and Nextflow just starts running. It's like an engine. And everything, it just runs. Usually not the first time, usually it takes a couple times to get it right. But then you get that thing working, and it's just beautiful. I really think that Nextflow and other workflow managers like it are really the next evolution of how we write code. Because the way we currently write code is basically like a recipe, right? Like just a single sequence of instructions, like do this, and then this, and then this, and then this. We call it imperative programming. Imagine that you had a giant recipe that was very complicated, and you had it all written out one step at a time, and then you had 4 people come in the room and say, hey, we want to help you, with this giant recipe that you want to cook. Is it immediately clear how you can split up the work? It's not at all, right? Because you just have everything in one line. What if you actually had a flow chart describing sort of not the data flow, but the food flow, the ingredient flow? Like, okay, you start out with these ingredients, and then you do this operation, and now you've got some bread, right? And then now that bread goes through that. And then you have this flow chart. Well, now it's actually very clear how much parallelism you can get out of that. And so now like, okay, if I have 4 people, I can split them up in this way. And that's sort of what workflow managers do for code, is that it allows you to describe the inherent parallelism in your analysis. And then that way you can, like I said, you can give it a laptop or a supercomputer or a cloud platform, whether you've got 1 core, 8 core, or 1 million cores, CPU cores, and it just automatically scales to the compute capacity that you have. I'm having trouble even just describing all of the different ways that it revolutionizes
You're doing a
things.
great job.
That's probably the main thing. Just the expressiveness and sort of the automatic parallelism. And my hope is that honestly, that this paradigm of programming can actually be expanded to all levels of coding, not just like these very high level analysis writing, but even when you're writing, the tools themselves, when you're writing in C++ or Java or Python, whatever language that you're doing, that we actually develop ways to describe code more like flowcharts rather than recipes. And that I think will both be a lot more accessible for people who aren't experienced programmers, because it allows you to sort of think more like a human rather than a computer. And then it will also be better for the hardware that we're using. So as the hardware gets faster, as it scales out more, our code will scale up with it. So
Yeah.
that's all I'll say for now.
What's your opinion on like how hard it is? Because like writing code like that's like an impossibility for some people that have never done it, and that has different meanings, I guess, for different people. But like a workflow manager, Nextflow, for example, like it's writing code, right? But it's not like, is it harder than writing like a application, or is it more intuitive? I love the recipe concept too, and that's basically what you're doing is ordered events.
Yeah, I mean, I think the ideal is that it's much more declarative, basically, which is why I think of it as being much more human friendly than machine friendly. Because
Right.
when you write imperative code, like traditional code, you literally have to think like a computer. You have to be like, okay, if I'm a computer running this program, I'm going to do this and this and this, and here's all the different variables they're changing. It's very difficult, even for experienced programmers. But when you're using a workflow language, the difference is that it becomes declarative. So you're not really writing up a recipe. You're more like describing, like, here is how this thing flows to the next thing. It's very similar to like if you were describing like a physical structure, saying like, okay, like describing like I don't know, like a building or a network of roads or something like, okay, this road goes through this way and then these two roads connect here and stuff like that. It's just like that. You're just describing this task and then the next task and the next task, and here's how the data is flowing through all of that. And it's much closer to if you were to ask a scientist like, okay, here's this big analysis that you do all the time. How does the analysis work? They would say, okay, well, you start with this first step and then you go to the next thing and so on. And it's a lot closer to that than writing literal code. I hope I answered your question.
Yeah, and jumping into that, so you've worked with a lot of different fields, right? Like you've worked with me in biology and other fields. Like, do you find that you've probably worked with a lot of people too since you've gotten your job, I bet. But do people know what they're doing a lot of times? Like it seems like this is something that really a workflow manager helped me understand what we're doing. Like I know parts of the recipe, and I have to go look at different pieces and throw it together and make it happen. But then, like now I know where I can optimize and things like that. Do you find that people are as dumb as me and knowing what they're doing, or inefficient, or just, I don't know, ignorant of what their workflows are in the computer?
In my experience, it seems like the path that most people take, like the path that leads most people to tools like Nextflow, is like I said earlier, the first natural instinct is to write a bash script, because that's sort of the first thing that you learn when you're learning how to use, like Linux and the command line and things like that, is like, if you want to automate something, just write a bash script. And we don't really teach workflow languages as like a first order like tool yet.
Yeah.
And so people sort of wallow around in bash land for a while until one day maybe a colleague tells them like, hey, have you heard of Nextflow? Have you heard of SnakeMake? And then they discover it and they have that aha moment that I was describing earlier. They're like, whoa, this is like the next level kind of work. I would say that I suppose that the declarative styles of programming, and really functional programming is really what it is, tends to be a lot more stricter syntax-wise. But it's usually a good thing, because what it means, there's more guardrails, there's less ways for you to sort of screw yourself over. So, a lot of times when you're trying to write a pipeline, write up the pipeline script, you know, it'll force you to really think about
Hmm.
what your analysis is. What are the dependencies between everything, and if you don't think through those things, then it just won't work. Like not it's not like it'll run and have like these silent failures that happen so often in normal code. It's like,
Right.
no, your script is invalid. You've got a problem here. You need to fix this before you've even run anything, right? So in that sense, I think it is more helpful for scientists, for not non-technical sorts of scientists. I will say though that in the short term, Nextflow can be difficult because it's written in a what I think is an obscure programming language called Groovy, which is it's like a scripting language based on Java. It is very powerful. It's just not a lot of people know it. So a lot of times people come to learn Nextflow and they have to learn Groovy at the same time. Whereas if it was written in something like Python, a lot of people are more familiar with Python, or even R. A lot of people use R. And so there is a learning curve related to that. But overall, I think it is a very worthwhile investment. I'm not saying you have to learn Nextflow, but I'm saying pick a workflow manager and
Right.
learn how to use it. Learning a workflow manager these days as a scientist is as important as learning a scripting language. It's going to be an especially important thing.
And to be able to tap into that, like in my lab, everybody's got to know this on some level, at least send some programming to get out and do biology. But I mean, how accessible is this to people that don't know any coding? Like, do they need to learn how to use the command line? Because I mean, there's so many people that are used to swiping left and right on their phone. I guess that's like a dating app kind of thing, right?
Right.
Or
Yeah.
whatever. But I'm old. But how much training and I'm sort of like loading the question because I have a strong opinion on this. But like, how accessible is this stuff to people? I mean, there's no reason to learn this if you're not ever going to use it. But when you're doing science and research, you pretty much have to use big computers now to process big data sets. But how do you get over it's impossible, I can't do it? I always think of like, I can't do math. I remember people when I was a kid saying I could never do math. And that's absurd.
Yeah.
They can do math if they just do it.
Yeah, a lot of times it comes down to, how you're taught. People learn different
Yeah.
ways.
Mhm.
There's a lot of really cool ways to learn math that probably don't get taught often enough. That's kind of how I feel about workflow languages, honestly.
Yeah.
I guess there's two levels to it. On the one hand, if you want to learn how to write your own workflows, then yeah, you definitely need to learn how to use the command line. In part because a lot of the concepts of workflow languages actually derive from how a lot of the practices that we use in the command line. That really is the starting point for lots of, especially bioinformaticists, right? Is the first thing you learn is like how to cat a file, or how to filter it for
Right.
different lines and search it, things like that. So yeah, I think that's a very essential thing. Knowing how to build C++ applications with Make, and how to install these different libraries and get all that stuff to work, I don't think that's necessary. I think the tools should be very easy to install for people. And Nextflow is very easy to install. All you really need is Java, and then you're good to go.
Yeah.
But then beyond that, using the actual command line, I think is very important for that aspect. There's another level to it, which is that there is a subset of scientists who will never have to write their own pipelines. They will only ever run pipelines that other people have written. So,
Right.
for example, Nextflow, we have a community called NF Core, which has basically been building out all of these sorts of standard bioinformatics pipelines that people use. For example, there's one called RNA-seq that's just like sort of a Swiss Army knife of
Right.
RNA-seq analysis. A lot of people, they're not going to need to roll their own RNA-seq workflow. They can just use the NF Core standard workflow, and there's like a million ways to configure it. So very likely it can fit your use case. And so the important thing there then becomes just all the things around that. So, how do you load up your input data? How do you manage your compute infrastructure to actually run the pipeline and then get the output data from wherever it was produced? And that's a big part of what Sakara Labs is doing with Nextflow Tower is sort of creating basically a web application that brings all that together, so that for
Right.
users that aren't writing their own pipelines, that are just running workflows and just need the inputs and the outputs, just making that as easy as possible. So you have this one location where you hook up your compute environment, your storage, both for input and output, and then you basically tell Tower like, hey, run this Nextflow pipeline. Here's where it's located in GitHub or GitLab or wherever. Run that, and then here's a cloud provider that you can send all the jobs to. Here's an S3 bucket or whatever object store bucket or whatever that you can throw all the output data into, and then when they're done, they can just download it, or they could do whatever. They could spin up a Jupyter notebook on top of that data and do whatever other analysis they want to do. For them, it's possible for them to do all that without writing any code, right? Because everything is sort of prepared for them. And so obviously that's not everybody. Like some of us have to write the workflows, and a lot of people need their own custom analyses. And so in that case, they have to pull into those deeper skill sets. But for the people who just need to run stuff, I think we can create sort of a happy path for them. So,
do you think there's a lot of people like that? Because I always find that something breaks a little bit, and then you have to have at least some technical skills to be able to go and edit a text file, right, to make it work, and even to the point of like real basic stuff, which is very challenging for newbie people in this area, is just like how to find where the file is on the file system. And sometimes you can just go and remap, where that goes, and like, I don't know. I just know that there's this. This is one thing that Praxis AI and I've been trying to do for years, even before Praxis AI, is just enable people to be able to troubleshoot, because that seems to be 80% of what we do when we're doing bioinformatics and computational biology research. It's not like we're sifting through are the results good or bad. It's like we got to get results. We got to get the recipe. We're missing an ingredient. We got to like replace it.
Yeah, that is sort of the hard reality these days of running these workflows, is that, as long as Nextflow has been around and as many people have worked on it, I still think it's very immature. Like I think most workflow managers out there are still very immature, just because of how, one of the biggest things is that, Nextflow you can run almost anywhere, which means that, for every new place where you can run Nextflow, there's a new vector for ways that things can go wrong and break. There's sort of this black hole effect of, people. So I've talked about how, people start out with Bash, they discover Nextflow, they get super excited about it. They start writing their own pipelines. They start having issues, usually related to like, hey, I'm trying to run it on my university cluster, and there's these weird behaviors with it. And so they get involved in the Nextflow community, right? And they'll submit tickets and all this stuff. And, sometimes people have encountered their error before, and they say, hey, here's how you fix it. Sometimes they're the first one. And so they're like, okay, well, if I don't fix this myself, nothing's going to happen. And so slowly, you slowly get dragged deeper and deeper into the community, both in terms of like knowing how to debug workflows, knowing how Nextflow works internally. And then there's sort of the ultimate level is where you're actually contributing code to Nextflow itself. This was my path. I tried for the longest time to get things to work without ever having to contribute to Nextflow myself, because I knew that if I had to download this giant code base written in Groovy and learn how to use Groovy in Java again and get all these tools to work, that would just be a whole other thing. And I did not have the bandwidth to do that, right? Because as you know, Feltus, I'm already writing these like multi-node GPU applications and writing Python code and Jupyter notebooks and all this stuff. I don't have the space to get into Nextflow contributing. But then finally at the end of my PhD, that's what I had to do, because it's like, well, it's my PhD on the line now, so I better make this work.
I better go learn Groovy.
So that's what happens. A lot of people may start out just as like basic users, but as they get drawn into the sort of the Nextflow black hole, and again, it's not just Nextflow, it's every workflow manager out there has its own black hole. You slowly get drawn into like out of necessity. Learning how to diagnose things and how to fix things. So, there's that too. I think anybody who gets into this field should be prepared for going down that path.
So I'm a little bit curious then, Ben, where's the magic, right? So we talk about biodata, AI, and workflows, and we started off with workflows, and now I think everybody has a much better understanding. I know I do about the critical role they play. Is the AI, is the magic in is the AI in the workflow manager, in the way that the data is being analyzed? Is it the as Feltus would say, the hypothesis or the experiment itself? What data you're looking at. I mean, the workflow is a mechanism, but is there intelligence in that mechanism, or is the AI and the biodata somewhere else?
Yeah, I would say that AI is a totally separate technology that we use aside from the workflow managers.
Okay. So it's not
thankfully, thankfully, there's not really any AI involved in workflow managers, because that would be a nightmare. I think workflows are complicated enough as it is, but they are certainly related in many ways. So with AI, at least from my perspective, having been a software machine learning engineer who joined the Feltus lab, basically seeing the different kinds of scientific questions that these students in the Feltus lab were trying to answer, and basically seeing okay, well, I've used these AI tools, I've trained neural networks to classify different types of images. This was the first thing we thought of immediately. It was well, why don't we just take that same image classification network and apply it to genomic data, just classifying different types of genomes, right? And we immediately saw okay, well, there seem to be different types of cancers out there. They have different genomic profiles. Maybe we can train a classifier to tell the difference between them. And that part was actually really easy. I mean, that happened almost immediately. It's it's actually very easy to distinguish them. But then the next question became okay, what are the factors that are causing these different tumors to be different? Can we find specific subsets of genes that are accurately describing the differences between these tumors? Maybe those genes are the reason why the tumor is developing in the first place. Maybe that's a potential pathway. Not a 100% answer, but it's if you can narrow yourself down from 50,000 genes to 10 genes to explore, well, that makes a scientist's job very easy. So immediately when we joined the lab, when Colin and I joined the lab, it sort of opened, there was these floodgates that opened of all of these different sorts of questions that we could explore using AI tools. That's the main way. So using AI tools, basically in the same way that you would use traditional statistical tools to try and extract insights from your raw genomic data, except now these AI tools can handle a lot more data, maybe handle more complex questions. But ultimately, you're still kind of using them in the same way. And then there's also, I guess, the other side of it is, well, not the other side, but just the other thing that we would explore in terms of AI was using AI to aid in the actual execution of these analyses. So now we get to the relationship between AIs and workflows. Is that, well, you're running these workflows, and you need, this was, so again, here was sort of the gateway question, was okay, we need compute resources, we need CPUs and memory and storage and time to execute these workflows, but we really have no idea how much we need. It's okay, well, here's an input file that's 10 gigabytes. How long will that take for my analysis? Well, I have no idea. So what we did was okay, well, let's just run some analyses a bunch of times and collect the actual performance data, the usage data, and then sort of use the past to predict the future. And so that was the first foray of AI with workflows. And again, there's another pair of floodgates there with okay, well, you can use AI to to recommend resource settings, or maybe to detect if an analysis went wrong somewhere, or even to optimize the scheduling of resources. So if you have a university cluster and a cloud platform and 3 different cloud platforms, maybe your AI can sort of schedule your workflows across your different compute resources in an optimal way. There's all sorts of questions like that also open up. So I would say those are the 2 main connections
That's
that
great.
we had with AI. There's two different aspects.
Yeah, I think that one thing to add with that, just as a practitioner of this, is that the data sets are huge and they have to go onto big computers. The computers now, a lot of them are distributed. They're not like one, like a laptop where everything's done on one computer. They're networked together like campus computers and the cloud computer. And so you need workflow managers to be able to throw jobs at these resources that can be very expensive, especially if you're using like the commercial cloud providers, where you can with one genetic experiment, I could give me 5 minutes and I'll design a genetics experiment that I can spend $5 million on in a day. And then a lot of times I'd say if you're lucky, like 5% of your experiments are useful to go to the next step. They're all useful on some level. And so, I mean, think about like if I were a small lab in a university in South Carolina, that, if all of a sudden I get $1 billion bill, at the end of the year without having any management of my resources, and AI can do that management, then, I'm going to get fired. I'm not going to be able to do any science. And so what Ben's talking about, being able to have AI control the flow of data on finite resources, the data sets get ginormous. I mean,
Yeah.
I bet you I'll probably retire in 20 years, and I bet you will be heading towards exabytes of data, which is, there's only a handful of people that can even do those experiments right now, even with all the sophisticated tech. So we can't just brute force it, right? Ben, would you agree? I mean, part of this is adding finesse, and I like what you said, that this is real early, right? It's not, the finesse isn't baked in as deeply as it could be to be able to scale up. And it's just, when you scale up, it's unbelievable the patterns you see. If you look at the toenail of the elephant in the oasis, you see something, but then you look at the whole oasis and maybe all the oases, in North Africa, and then it's like, wow, what you discover.
Yeah, for sure.
So tell us a little bit about some of the other. Are you working with other kinds of science? I know you've worked with Alex and BioSciences. I imagine this would have an application in biochemistry or chemistry or physics or any other kinds of applications of this workflow technology in AI.
Yeah, so when I was doing my PhD, the Feltus lab in life sciences was definitely the biggest piece of the pie by far. There was a couple of other labs that I collaborated with a little bit, like material science was the main one. But that one, we weren't really using workflow managers. That was more just about writing GPU code. So just sort of some more like low-level optimizations. I think life sciences was the only one I worked in that was really using workflow managers. I don't know that the other science fields have really gotten into this space yet, or really discovered this secret. I've heard that there are some workflow managers that people use in like linguistics, which kind of makes sense because it's also like large text data. A lot of the more like physical sciences like physics and the kind of stuff that typically runs in the DOE labs. I think they still have their traditional methods. Just like write a giant MPI application, very like rigid parallel structure, and then run it across a giant supercomputer that has a very regular structure to it as well. And for them that's important because they want to get every ounce of performance that they can out of their computing. It may very well happen that in the future they will also converge on workflow managers like these. The only other big field that really uses workflow managers, I would say, is the sort of like I don't really know what the best word for it is. It's just like maybe it's data engineering or just ad tech. Really, all the big tech companies that have these hugely popular websites, and they have a lot of machine learning workloads around like analyzing user engagement or like content. So like YouTube with videos or Netflix with movies and shows. They're doing all sorts of machine learning work, analyses on the data that they have. I heard a joke the other day that that Netflix is is described as basically a metrics generator that occasionally streams movies.
Yeah.
So a lot of these tech companies, they're generating just so much data out of just so much like metadata. Aside from the actual content itself, just the data about how users are using their tech. They're using machine learning workloads all the time, and they have their own whole world of workflow managers, entirely separate from the ones that were developed in the life science community. And what I'm really interested to see is if there's ever any crossover between these two worlds, because you could totally use Nextflow to run, like some random machine learning workload at Facebook or Google or something like that has nothing to do with life science data. The workflow technology is exactly the same. Now, it might not be your preferred language. You might prefer to use Python instead of Groovy. and in fact, most of the machine learning workflow managers out there are written in Python. But those technical issues aside, it really is the same technology. And there is a lot of potential for crossover. I haven't experienced that yet. I'm hoping to. I would love it if Sakara Labs could expand beyond just life sciences and actually get to, basically anyone who are like, if you need to run a workflow, come to us because we're your guy. We can do it for you.
All in one place. Yeah.
There is a common denominator with, image analytics. I mean, I learned this from working with people like you that, you can use image analytics techniques in biology. And if you think of things as if you can convert it into an image with, number of pixels and density and color and stuff like that, if you can use that analogy when you're doing it, it makes things really good. But I've noticed that there's a little bit of crossover between astronomy and biology. Actually, some meetings that happen together because they have the same data storage problems, distributed compute problems, and a lot of it's image analytics, because when you're doing DNA sequencing, the first thing you do is take a bunch of pictures of your technology and then translate that into ATGs and Cs of DNA. And so it seems like you could, if you have an image analytics workflow, that it'd be very easy to port across disciplines if people are aware of it and talking, right? Because these communities just don't talk to each other a lot, but I have seen it happen. And it's pretty exciting to think about, when you start translating workflows between communities, and then, it worked, and what else can we do? And that's one thing I've learned from doing interdisciplinary work. It's just amazing what happens. You don't know what's going to happen. You just know it's going to be awesome.
Yeah. This is why I think that, workflow managers are not just going to change how we do science. It's really going to change how we code. So really any application domain that involves coding, I think is, over the next decade, 50, 100 years is going to be transformed by this sort of new paradigm of how to write code, because you have to, in order to keep up with the amount of compute that is available, you have to be able to write code in a way that can actually, utilize all of that. So
go ahead, Alex.
I was gonna. So, what would you do if you're coming out with a bachelor's degree, and you wanted to do computational work? I don't know if I want to define it too much. Like, if you want to use computers to do stuff, maybe start a business or do science or whatever. Like, what would you rank as the top 2 or 3 skills? I mean, do you go through a computer science curriculum, and do you learn some things maybe they don't teach in computer science, like workflow managers? Like, how would you, knowing the wisdom that you have, like, if you want to train yourself to be yourself again, like at the undergraduate, getting a bachelor's degree level, what do you need to do? What do you need to know? What skills do you need?
Yeah, I suppose there's multiple ways to get to it these days. You ask about like what major. I mean, you could probably do it through a computer science major or through, more of a hard science major where you sort of pick up the pieces as you go. But in terms of being able to like be a biohacker, I guess, probably the first thing I would say is just learn Python. Like that is absolutely the first thing. Just learn Python, even if you never end up using it. It's just a great language for learning things, and very likely you will end up using it because it's got tons of good libraries, and people call it the Zen of Python. There's just a sort of a peace that comes over you when you write in Python. That's just me.
You definitely have a peace. It's that jazz Python,
and then
live in the jazz.
And then like learning Linux and the command line, learning how to use just all these. There's like a Swiss Army knife of these little command line tools for manipulating text files and things like that. That's a whole sort of skill unto itself. I guess learning to use Google and Stack Overflow. That's honestly the way most people learn things. Is like you want to write something in code, and maybe you already know a little Python, but you're like, how do I do this specific thing in Python? There's a 90% chance that if you just Google that, you'll find a Stack Overflow page with an answer with a green check mark, and it's like, well, there's how you do it.
Mm-hmm.
Now, of course, the eternal caveat is that don't just copy code that you don't understand.
Oh yeah.
But what you can do is you look at someone's answer and make sure you understand what they're saying. And a lot of times it is very straightforward, and it is just like, okay, take this code snippet and apply it to whatever you're doing. So that's a huge part of it, really, is like not just knowing stuff, but knowing how to find stuff. You
Yeah.
understand the internet is like this giant sea of information, like a giant, like, I don't know, like a gene correlation network, and you're just swimming through all these different nodes from one website to the next, trying to like, okay, how do I find the information that I need? Knowing how to navigate the web is extremely important to that as well.
Huh.
And then, yeah, learning a workflow manager, which again, not necessarily something you have to learn right from the get-go, but maybe once you get to the point where you're trying to, maybe when you're learning about actual analyses that you want to run, whether it's like how to train and use a machine learning model, or you're actually learning about different ways to process genomic data. Maybe once you've got to that point, then and you start to understand sort of the multi-step and parallel nature of what you're trying to do, and then just sort of keeping workflow managers in the back of your head, saying like, okay, when I get to this point, remember this, and understand that the workflow manager and the pipeline is how you express those kinds of things. And then, the nodes within the pipeline will be, Python scripts or whatever you want. I suppose, so that's sort of the coding aspects. And then in terms of like the environment aspects, so I've talked about Linux, and then I guess there would be, I think Jupyter Lab is probably sort of a universal tool that everybody would benefit from knowing. And just understanding how you can spin up a Jupyter Lab instance anywhere. You should be able to spin it up on your university cluster or in the cloud somewhere. And there are even websites that'll just give you one for free.
Praxis AI.
Yeah, there's one for you.
Yeah.
So now you've got, it gives you the best of both worlds, right? Because you can get these interactive notebooks. So and that's another thing, I guess, is learning how to use notebooks. But then you can also still pull up a terminal. You can browse all your files. All that stuff is still there.
Yep.
So it's very versatile in that sense. Learning how to use like a HPC scheduler, or how to use the cloud like on a very low level, I would consider those more advanced topics. So get into those if you want. But be on the lookout for sort of more abstract ways of doing that. So, maybe you land at a bioinformatics startup or a big pharma company who uses Nextflow Tower, and it's like, okay, well then you don't actually have to worry about how to like spin up an EC2 instance on Amazon. You just got to know how to like log into Tower and then, set up your compute environment, which is just going through a menu and then running pipelines. But knowing some kind of abstract way to use the cloud, whether it's through Tower or some other sort of abstract tool, would I think also be very useful. And then beyond that, I would say that's all the sort of like the generic skills, and then beyond that, it's just sort of the domain specific skills you need, right? So what types of data sets are you working with, and what types of analyses are you going to be using a lot? Familiarizing yourselves extremely well with those things, especially your data, like the data structure. You can never like understand your data too much. There's always a benefit to making sure that you understand the nature of your data, how it is being produced, what are the different sources of error, all those kinds of things.
It's a lot.
Yeah, no, it's exciting. And I think, I was checking the boxes in my mind as Ben was talking, Alex. That all those things are in your journeys. I mean, in the Praxis AI BioHacker journeys, a lot of the BioHackathons, are going through each of those skills, and those are also cataloged in the BioHacker credentials, the digital badges. So. In wrapping up, Ben, we always like to ask, you're one of the original biohackers. Thank you very much for joining the community. What is a biohacker to you?
I would say that biohacking is a big tent. So there probably isn't just one sort of specific profile of what makes a biohacker.
Right.
Like, for example, I don't consider myself like a scientist, like a bioinformaticist or a biologist or any of those things. I never really like I took ninth grade biology, and that was it. So I really don't have a background in those domains or any other science domain for that matter. I'm just a software guy, a workflow guy, an AI guy, and I partner with other domain scientists to get things working. That doesn't mean that a domain scientist can't learn these programming tools. I think they should for all as much as they can. But there is and that so perhaps that leads us to saying that there's sort of two complementary roles, right? There's
Yep.
like the people who are primarily domain scientists, and they have the domain knowledge, and they also have as much technical knowledge as they have the bandwidth to get, right? And the more they get, the more power to them. But
Yep.
ultimately, there also is a second role of the primarily technical people, the people who know how to write workflows, know how to apply different AI tools and reason about them, and even people who are skilled in infrastructure. So like knowing how to provision resources in the cloud and or on your university cluster, things like that.
Yep.
And these people support the domain scientists. And maybe we'll reach a future where we are actually obsolete, and it's actually possible to be both a scientist and have all the tools that you need. But for now, at least, and I'm very glad for it. There are both roles, and there's sort of a yin and yang to it, and they work together, and together we're able to accomplish way more than either of us would individually. So it's a very beautiful and very useful arrangement.
Yes, kind of like a jazz combo. So
Yeah, that's a really good. Yeah. I mean, one musician can play some good music, but you get some people together, and the interdisciplinary synergy starts to set in, right?
Absolutely, yeah. There
It's
is no
magic.
comparison. It's a
Magic.
whole other level.
That's the magic.
that's the magic is in the collaboration and the synchronicity between the different players and people playing different roles. And I'll end on something that Reed said in one of our previous podcasts when he was talking about a tuning mind, and he said that when band members come together and they're playing a particular song or a particular piece of music, their brain waves synchronize because of the oral feedback, etc. So I think in many ways, when biohackers are working together, both from the purposes of domain science and the computer science, they're synchronizing their brainwaves so that 1 + 1 = 19 instead of 2. So great segue. Thank you so much, Ben. It was a wonderful podcast. We really appreciated hearing from you. It was riveting. And we'll see you around. Do the closing song.